Next, we have a contribution from the Extreme Robotics Laboratory. So they're based at the University of Birmingham, and they spend a lot of time researching new ways to control robots, but also for extreme conditions. So, for example, in the nuclear industry and handling dangerous items. So really pleased that Chris Gell has been able to join us live from the University of Birmingham this morning, and he's going to explain a little bit about the research that they do, and also, I think, technology permitting, he's going to show us some of his laboratory. So we're going on a little bit of a virtual lab tour as well. So hi, Chris. Thank you very much for joining.
Hi there. Thanks for having me. It's a great pleasure for me to be here. So as Adrian mentioned, we work at the Extreme Robotics Laboratory in Birmingham, mostly dealing with extreme environments that are hazardous for people to be in. Ideally, we like to send robots in there to occur situations for us. The big thing with robotics is, we see in industries like car manufacturing, warehouses where you see pick and place. These days, you may be seeing things on the Amazon warehouses where they're going around picking up packages and items and distributing them. That's all very much kind of pre-programmed set motions. The robots don't tend to be very aware of their own surroundings. They're just given a set kind of, here's where you start, here's where the task is, and then this is where you finish. And they're very good at doing high repeatable tasks that don't have a lot of variation. So what we do here in the lab is we're trying to introduce the robots into unknown scenarios and try and teach them to interact with them autonomously without too much human interaction. So, for example, two of the main things that we do in robotics are down to control and vision. Control is where you set up algorithms, control systems to move the robot in a way that it's comfortable and it can do the task it needs to. And vision is a way of letting it see its environment and understand what it's seeing. For example, if you had a few objects on a table and you use special cameras to image that table, until you teach the robot what it's looking at, it will just see a single surface with varied geometry. So it won't see a pen on a table, it will see a surface with a kind of a cylindrical distortion on it. It doesn't understand what it's seeing. So a big part of the programming here is teaching the robot to understand what it's seeing and how to interact with that. And then when it comes to the extreme environments, you also have to consider, when we work with the nuclear industry, we have to consider ways of dealing with the radiation that's involved. If you're not aware, a lot of the radiation involved in nuclear decommissioning is actually damaging to electronics over time. So we have to think of ways of shielding and detecting that radiation so that the arms can do the jobs they need to do. And you may not be aware of this, but when it comes to nuclear decommissioning, there is still a large majority of it being done manually by people getting in big big plastic suits and spending a few hours a day cutting down old nuclear waste and sorting into barrels. And it's all being done manually by hand by people that spend a few hours a day in these suits. Whereas we're now trying to get robots in there and handling that for us. But obviously, until the robots can identify what they're working with and work safely, it's very dangerous to just leave an arm unsupervised dealing with this waste, because obviously serious accidents could happen if they don't know what they're doing. We also look into what we call semi-autonomous systems. So, for example, one of our researchers who work with mobile robots, they're working on a system where, for example, a search and rescue might be taking place, where you have a mobile platform with an arm that can manipulate rubble and so on, and a camera can go into a building that's not safe for humans to go into and start searching for, potential injured survivors that are still in the scene, where there are times when the operator can become distracted. Maybe the sent reports they have to look over, or maybe they're relaying information backwards and forwards. And we have a system that the autonomous system will detect when the driver becomes distracted, and it will take over and start automatically planning and searching. And then once the operator's got back his concentration, he can then take control back over again. I'll actually show one of the platforms that we have that's being done at the moment. Myself, I'm actually the head technician here at the lab. My main job is to do with ordering, maintaining, checking equipment, but also designing and manufacturing prototypes. So if the researchers here have an idea in mind that want to do something special with the robots that haven't been done before, they may not have the tool or the equipment available to them. So they'll ask me, okay, this is what we want to do. Can you design something to go on the arm to make it happen? Or can you make some kind of interface between the arm and the tool that we have to make them work together? So I've probably got one of the least interesting jobs at the lab, but it's still a pretty fun one in my opinion. So what I'll do now is I'll just try to tool you around the lab. Using a laptop camera is going to be a bit weird, but I'll do my best so you can have a good view. So where I just started from, this is the human interface area, and it's mostly to do with coming up with novel ways of controlling robots. We make virtual environments so we can run simulations. We can use the virtual control system to manipulate the arms. Traditional ways of controlling arms tend to be with joysticks, and it can be very cumbersome and difficult because you have to move the robot axis by axis, which is very unintuitive to most people. So we're looking at ways of making 3D environments so that people can jump in and more naturally control the arms. The next area, we have one of our biggest arms in the lab. This is a Kuka Robot, which is a company in Germany. This is one of the more industrial arms that we have. And this is called a KR16. The 16 indicates the payload that it can have on the end of the arm. This includes any tool that it has to work with, any cameras, sensors, etc. And then the actual load it interacts with. Because it's a more industrial version, you can see that the motors are exposed, there's a lot of sharp edges, the cabin's all exposed. This is designed to be left to work on its own without any kind of human interaction. This is the kind of arm you'd probably see in assembly places, manufacturing, that kind of things. They're just left to do the work that they've been programmed to do. There's another type of arm that we have that we call a cobot. These arms are specifically designed to work alongside people. They have sensors built into them that are safer to be around humans, so they have like impact sensors. So if it knocks into somebody, it will stop the arm dead, so that there's less chance of it running into somebody. An example we've got here is another Kuka. This is an LBR 14. So you can see that all of the motor housing is covered up. Everything's quite smooth and ergonomic. The idea is there's no pinch points. There's nowhere that if it does hit into you, there's going to be any kind of damage done. These are specifically designed to work around people. We've also got a very special gripper here. You can see these little pads on the end. These are actually tactile sensors. These are designed so you can actually see how much force is being applied by the gripper. It can detect what it's picking up. It can tell when it has something inside the gripper, which most don't. They normally have a set amount of pressure they apply, whereas that one specifically is designed to have feedback and know when it's interacting with something. And you can also set the tolerance on how tightly you want to grasp something. So if you want to pick up something particularly delicate, you can set a limit to how much force it will apply. Just a moment. The next thing we have here, now, if I can just get it in view, this little device here looks like a little miniature arm itself. This is actually a haptic feedback controller. So the idea is you can take hold of it once you've programmed it in, and you can basically get feedback from the arm. So if you program a path, the arm will want to follow that path, and you can guide it in using the controller, and it will limit the movement so it only follows the path you've asked it to. But you have control of how fast it goes in, when it picks something up. What it can also do is, depending on the arm that you've attached it to, is it can tell you when there's some kind of resistance. So you physically feel that coming back to you, which is another unique control method we've got. Next, we've got the small engineering area, which is where I do a lot of my work. So we have a small array of 3D printers, one of which is actually off-site at the moment due to the home working. Little pillar drills, my workstation, and just an area to do any physical work that I need to. So this is where a lot of my prototyping would happen. A lot of the design elements using CAD software to generate models, print them. If we can use them as printed models, we will. Otherwise, we take it down to the machine shop downstairs and they machine it for us. One example is, this is a disc cutter that I designed to go on the end of an arm so that we could do some cutting using a robot, which was a difficult process to go through, but it was good fun. We've also got another type of arm here. This is a universal robot, the UR10. Again, designed to be a cobot. You can see that most of the ones designed to be around people are quite a sleek design. So they're meant to be not too dangerous to be around people. We're now in the mobile area. So what we have with mobile robotics is you have a mobile platform, which is an independent robot of its own. Then usually you have another arm sat on top of it, and then some kind of gripper or camera or some way of interacting with the environment. So this down here is the TailRob mobile platform, and the arm attached is Schunk arm, which is another company from Germany. Here we have the Kuka mobile platform. You can tell there's a lot of Kuka here, but it's one of the better companies that we work with. So this one's got a mobile. This mobile platform has sensors built into it. So there's a lot of factories in Germany that use these alongside people. They'll set routes for it, but it's got sensors so that if somebody walks in its path, it will stop and wait for them to go, and it will carry on with its program. And you can see the arm attached as well, another cobot arm. And then over here, this is a Husky with another UR arm on it. If I can just get it in view. And this one's a little bit more robust. This one is the one we mentioned. We're talking about this semi-autonomous system. The system is designed to run on the Husky robot. It's got nice big rubber tires, big sturdy platform, very easy to work with. This is why we have it in the more dangerous areas where we think there might be some damage, potentially, rubble falling, running into obstacles, etc. That can handle it quite well. We also donated the Dalek for some reason, but this is one of our more famous parts of the lab. We also have an extra platform down here. Now, this one was actually designed and built by the professor that runs the lab, Professor Rustam Stulkin. So he made that entirely from scratch on one of his previous projects that he did. And then typically in a lot of our experimental work, we'll do these safety cells. Inside we've got two Franca robots, which again are designed to actually be manipulated by people manually. They've actually got a teaching system where you can grab hold of a control mechanism on the end and manually move the arms around yourself without having to use the programming software, which is a nice little feature. And again, another cell here with a Kuka and another universal robot. This is actually for a research project we're doing in conjunction with the Faraday Institute, looking at ways to recycle the batteries that are in electric cars. Because if you don't know, lithium-ion batteries are somewhat explosive if they're not handled correctly. And if they start to burn, they will burn until all of the chemicals are used up. You can't really put out a lithium-ion fire. It's just kind of wait for it to finish and then come back and get it afterwards. So we're looking at using the robots to dismantle these large casings, take out the battery cells and strip them down to the individual cells, and then looking at chemically recycling them. And that's one of the things our robots are doing at the moment. I'm not sure how I'm doing for time.
Yeah, no, you're pretty much on time. So I don't know whether you've reached the end of your tour. You've certainly covered an awful lot of ground there, which is fantastic.
Yeah, I tried to be as quick as possible, but if people want more information, I'm happy to answer any questions that they might have. It was a very, very brief kind of overview of a lot of the work that we do here, just to give an idea of the stuff that we work with and the kind of challenges that we face.
Yeah, no, that's fantastic. And of course, you know, a lot of the people at schools won't have any idea necessarily what it's like in a, well, university research laboratory or a high-tech lab. And as you've just shown us, you know, it can be a really fun place to work. I noticed that John Palmer, who's at the Chase School, said and I think you chuckled when you saw it, that robots are cool. And, you know, for the students that are thinking about a career in science, maybe doing some physics, some electronics, some computing, all of that can be applied to robotics, and you could end up working in a lab a little bit like you've shown, or working in industry with these kind of robots. So it's really fascinating. I don't know what the population of robots in the world is, but it's although it's several million, I think it's not particularly high when you consider how many people are in the world. But I think that's going to change as well, isn't it?
Yeah. So one of the biggest problems that we have with robotics is people are resistant to change a lot of the times. There's a lot of industries and environments where robotics would be ideal for it, but you always have the phobia of a robot's going to take my job. I don't want that to happen. But conversely, what you could actually end up happening is the people that work in these industries can be retrained. So rather than doing the boring, monotonous job that they do at the moment, to be trained to actually handle looking after the robots themselves. So for example, one of the most common uses of robots is welding, just spot welding for like vehicles that are being manufactured. You could be a welder that just sits there and tack welds the same part of a car over and over all day, or you could be in charge of an assembly line of arms doing the same job for you, which is quicker and cheaper for the company, but also you get a more interesting job out of it at the same time.
Exactly. Yeah.
And yeah, as you said, because the use of robotics is gradually becoming more accepted, the work and the employment involved around robots is going to be going up and up more over time. I personally didn't start out looking to do this kind of thing. I've had a bit of a career change over the years. And before I started working with the laboratory itself, I'd never even interacted with a robot before. So most of my knowledge I've gained over the last 2.5 years. I'm actually going for retraining myself. So I've been going back to relearn engineering, physics, etc., and hopefully be doing mechatronics. Mechatronics is a combination of electrical and mechanical engineering, which is ideal for robots. Most people will specialize in one or the other, but this combination of the two is becoming far more common these days, especially with computers becoming more involved, etc. It's an interesting time.
Yeah, no, it's really interesting, and yeah, it's going to be the future, you know. And so these sort of skilled jobs to program the robots, develop the robots, I think those are going to be really valuable in the future. So thank you ever so much, Chris, for joining us. Really good to see you. And you may well get some more questions in the chat from anybody that's watching.
Thanks very much. Thanks for having me.
Festival of Innovation.